So semiconducting materials we know are usually either silicon or germanium-like materials, but they can also be a compound semiconductor such as a gallium arsenide or cadmium selenide materials. These are materials that are actually alloys of two elements, okay, but they are semiconductors as well. And semiconductors materials we know can conduct electricity in one of two ways. One way is by using free electrons, okay, free conducting electrons, and we're familiar with that in the case of pure metals. Pure metals are atoms that come together with a sea of electrons that holds everything together, and those electrons are free to move around and therefore carry electricity. They are called carriers of electricity. So if the carrier is of electron type, then we call that an N-type material. Okay, so a semiconductor can be an N-type material if you have elements in it that cause a free flow of electrons. They can also, though, conduct with positive particles, which we call holes, and those holes are actually missing bonds between atoms, and they have a net positive charge. So the carrier then is called a hole. If we have current flowing in one direction, for example, if we have electrons flowing from the left to the right, okay, in the N-type material, if we have the same voltage across a P-type material, we have holes that move in the opposite direction. They go from right to left, okay? So that's the difference between the two. So what happens then if we take an N-type material and join it to a P-type material, where you've got electrons flowing on the N-type, and you've got holes flowing on the P-type material? Well, at the junction of these two, we create a barrier. We create the barrier because at that junction, the electrons and holes combine for causing a neutral region. Okay, it's actually an insulated region. We call that region a depleted region. It depletes of electrons and holes by the combination process. Okay, in depleting the carriers, we create a voltage barrier. Okay, so that depleted region has a voltage associated with it. In the case of silicon, that voltage difference is about 0.7 volts. And in the case of germanium, that voltage is about 0.3 volts. And gallium arsenide, cadmium selenide have higher voltage barriers, okay, which we can discuss at later date. Okay, but once we create that PN junction, okay, then we are ready to discuss how to make many other of our semiconducting devices. But today we're going to go through just the very simplest of these, which is the diode. And there are two different kinds of diodes that we can make using a PN junction. Just a regular PN junction diode as a rectifier, a small signal rectifier, which allows current to flow in one direction but not in the reverse direction of the voltage across the PN junction. Or we can actually, if the voltage is high enough, we can have the current flowing in the opposite direction, and that is the case of what we call a Zener diode, okay, where we intentionally have it go in the opposite direction. So today we'll discuss the diode and the Zener diode, the differences between the two, and the current voltage characteristics of such a junction. It's the forward bias versus a reverse bias condition. Forward bias meaning what happens when we charge the N-type side with a negative charge and the P-type side with a positive charge. That's a forward bias. If we switch the polarity, that we call a reverse bias condition. And we get normal conduction in the forward bias direction, and in the reverse bias direction, you can only get minority carrier current flow, which is very, very low current, until we have a voltage across that is very high, and the barrier breaks down in one of two different ways. We prefer to have it break down in the Zener breakdown mode, which then creates a characteristic voltage, which we can use for voltage regulation in special circuits. If, on the other hand, we increase it to a higher voltage and along with heat, we create a avalanche breakdown, which destroys the PN junction altogether and renders the device useless. All right. So we will investigate those characteristics, and their characteristics are basically the current voltage relationship, whether it's in a forward bias or a reverse bias mode. Okay, so let's get started on that.